First you separate, and then you integrate. Just follow these steps, and you will do great. First you separate, and then you integrate. Just follow these steps, and you will do great.
Here's the season to be serving.
When I was solving equations, I was feeling amazing.
Greetings. Today's video is about definite integrals explained, part 1. In this video, we're going to look at the definite integral explained in context of area under the curve. So let's take a look. So we have looked at area under the curve in the previous video, and that came with an approximation of the area under the curve. And when we say area under the curve, we're talking about the area underneath some function, which we'll just call f of x to the x-axis. And when we did the Riemann sum, and we used this base function, so this is the same function we use on the Riemann sum video, and this is a function 10 minus x squared, and we did a couple of approximations on its area using 3 subintervals for a right and a left Riemann sum. And this, for instance, is a picture of the right Riemann sum, and when we did it, we got an area of 16, and you can see here that's showing the 16 that we calculated. And the actual area, as we stated, is actually 21. So this is an underestimate, and you can see this white that is not getting the complete area. And we also did a left Riemann sum, which in this case gave an overestimate. And the right is given an underestimate, and a left is given an overestimate in this particular case, because in this interval that we're looking at, and by the way, I'm sorry, we were looking at the interval from 0 to 3 when we were finding these areas, because on the interval that we're looking at, the function is decreasing. And so when a function decreases, a left Riemann sum is an overestimate and a right Riemann sum is an underestimate. If a function is increasing, the reverse occurs. And one thing we talked about, I'm gonna go back to a right Riemann sum. One thing we mentioned, I think we might have also calculated the area at 6 subintervals, but the basic premise we explained when looking at those Riemann sums is the more subintervals I use. So here I'm just increasing the subintervals, and as I increase these subintervals, take a look at the amount of white as it lessens, and also take a look here at this area approximation as it gets closer and closer to the real area, which again is actually 21. And as you see, if you can just take a look at both those items, the amount of white lessening and this number getting closer and closer to 21, you can see the more subintervals, so the number I'm adjusting is n was the number of subintervals. The more subintervals I use, the better my approximation goes. And the fact is, actually, if I use an infinite number of subintervals, I will actually get the area. And I'm going to use an infinite number of subintervals, and that's going to give me the definite integral. All right, so when we did the approximation with the Riemann sum, this is kind of a sketch of what we looked at, and we defined delta x as b minus a over n, and delta x is the width of each rectangle or the length of each subinterval, and in this case it was 3 minus 0 over 3, which is 1. And here's the graph of f of x here, and you can see it hits the y-axis at 10, and of course f of x is 10 minus x squared, and it hits the x-axis at the square root of 10, which is just a little more than 3. And basically, to approximate that area with the right Riemann sum of 3 subintervals of equal length, we just took the area of these 3 rectangles, and the height of each rectangle, and again, it's for a right Riemann sum, the first subinterval is from 0 to 1, so it's going to hit the actual function with the point that's on the right of the subinterval, which would be 1. And from 1 to 2 would hit at 2, and from 2 to 3 would hit at 3. And so the height of each rectangle is the value of the function evaluated at 1, 2, and 3. So for instance, f of 1 is 9, f of 2 is 6, and f of 3 is 1. And those heights multiplied by the width of each rectangle, which was equal width in this case, was 1, which is going to be delta x in all cases when it's of equal length. And so that's how we found this particular area. Now, what we did here could be written in something called sigma notation, which signifies summation. And basically everything we did here, because again, to find this area, this area approximation, we basically did f of 1 plus f of 2 plus f of 3, and all those times delta x, which in this case was 1, so it didn't make much of a difference. And so this summation, again, f of 1 and f of 2 and f of 3, here I'm evaluating a function at a plus delta xi. So in this case, delta x is 1, and I are just integers from 1 to 3. And this 3 here doesn't come from the 3 from b, the ending of the interval, but the 3 from n, being 3 subintervals. So this 3 correlates to n, the number of subintervals. And, you know, a happened to be 0, so you have 0 plus 1 times 1. And for each iteration, I, goes up 1. So the first iteration, I is 1, and then I is 2, and then I is 3. So you have 0 plus 1 times 1, which gives me 1, f of 1. Then 0 plus 1 times 2, which gives me f of 2. Then 0 plus 1 times 3 gives me f of 3. And so that's how we had that. So this is a way of writing the process we did in sigma notation. And what I want to do now is just write the general sigma notation for this right Riemann sum. And again, for this particular scenario, we're looking at a right Riemann sum, simply because it's going to be a little easier to do, but it's still going to be a lot to do and pretty meticulous. But if we looked at left Riemann sum, once we get an infinite number of subintervals, the right Riemann sum and the left Riemann sum become equal. So in general, our Riemann sum is this guy. So in general, this is going to give us the value of our Riemann sum. So we're summing as I goes from 1 to n. Again, n is the number of subintervals of f of a plus delta xi times delta x. Well, of course, delta x is b minus a over n, where a and b are the intervals of the integration. Now, again, to get the actual area, we want to do an infinite number of subintervals. Again, n is a number of subintervals. So what we're going to do is we're going to take the limit of this summation as n goes to infinity. And I claim that's going to give me the area under the curve of f of x from a to b, which I have defined earlier as the integral from a to b of f of x and dx. So I claim that these two expressions are equal to one another. So let's go ahead and go about the good work of evaluating the left-hand side of this equation and kind of see what it comes to. Now, to evaluate this, looking outside in, take the limit as n goes to infinity. It's going to be something that's pretty simple. To do the summation, well, to do the summation reminds me, let me point out a couple of, 3 summation rules that I'm going to need to do this summation. And I think it's a good time to point them out now instead of pointing them out right before I get ready to do it. So these are 3 summation rules. One, if I take the sum of a constant as I goes from 1 to n, so say some constant k, that sum is kn. And I'm not going to explain why these summation rules are what they are. A lot of them are simple to understand. Particularly the first 2 I do are quite simple to understand, but I just want to have the time to explain why this happens on this video, because it's going to be a lot of time nonetheless. And another summation rule we're going to need to use, summation as I goes from 1 to n of I, that is n times n plus 1 over 2, or maybe it'd be easier to think of it as n squared plus n over 2. And so that's another one. This first one, I'm not going to explain, but it can be understood by common sense. If you take a constant and add it to itself n times, that should make common sense. And this guy comes from like the partial sum of an arithmetic series. And so if you look at arithmetic series, or our videos on arithmetic sequences and series, you can make some sense of this. We had a formula that looks very similar to this. If you understand, as I is numbers counting from 1 all the way to n integers, you'll understand why that's like that. And the last one we're going to use, and this one may not be so easy to figure out why it comes out the way it comes out, but again, I don't have time to explain. And this will be the summation as I goes from 1 to n of I squared, which is n times n plus 1 times 2n plus 1 all over 6, which is 2n cubed plus 3n squared plus n over 6. So those 3 summation rules, we're going to need those guys momentarily. So they're going to be of use for us. So when we do this summation, you'll see in a second, it's going to be a lot of stuff, but there's going to be some i's, and there's going to be some I squares, and there's also going to be some constants, which is going to require us to utilize these guys. Okay. So go ahead and do this. So what we have to figure out, and basically, and it's not as innocent as it looks, we're gonna have to figure out this guy right here for our particular situation. And as simple as that looks, that's going to turn to be a very long expression. This expression here, we already know delta x is just b minus a over n. So that's a pretty simple one. But this one's going to be fairly complicated. And then this one times delta x is going to be extremely complicated. And in fact, we're going to try to find a way to kind of get around multiplying this guy by all of delta x. I'll talk a little bit more about that when I get there, but let me go ahead and dive in. So just want to remind you of a few things, and that is f of x for this situation is 10 minus x squared, right? And delta x, as always, is b minus a over n. And f of a plus delta xi, the guy that I really want to find, is going to be 10 minus a plus delta x, which is b minus a over n times I. And all of that junk is being squared. Let me kind of make these parentheses somewhat of equal length. And so this is f of a plus delta xi. The only thing is to really find this summation and this limit, I'm going to need to kind of simplify this a little bit. And it's going to be somewhat of an oxymoron, because when I simplify this, it's going to get way bigger and it's going to seem way more complicated. But trust me, I'm simplifying it in a means of finding the summation and the limits a little easier. But it's not going to look like I'm doing us any favors, but I am. So, and I don't want to gloss over this algebra, and it's going to be some intense algebra that I'm doing. So I'm going to show everything I'm doing. I'm not going to kind of just go to the finished product. You should see work like this be utilized. So let me go ahead and go for what I know. So I'm going to do this step by step, and this is going to take quite a bit of space. So what I'm evaluating now is f of a plus delta xi, and so I'm just gonna move the equal sign a little closer to the end because of how long this expression is going to end up being. So let me first, so 10 minus a plus, so first thing I'm gonna do is just distribute this I. So bi minus ai over n squared. Okay, cool. So far, so good. And now I'm going to go ahead and square this particular expression here. So it's a binomial, kind of. Well, not kind of. It's a binomial, just with somewhat of a complicated binomial. So it squares quite nicely. So 10 minus. All right, so if I square this guy, I'll get a squared plus 2a times bi minus ai over n plus, and for right now, I'll just leave this as being squared. So plus bi minus ai over n squared. All right, so far so good. And the next thing I'll do is I'll just distribute this 2a here, and I'll square this guy, and then we'll get somewhere. And you can see, so when I do that, this expression is going to get even longer. And right now, it's really taking up the full length of the paper. So I'm going to write a little bit smaller. So let's go ahead and do that. Let's leave this in plain sight so you can see what we're doing. So 10 minus a squared. I said I was going to write smaller, and it looks like I'm not, but we'll be able to fit this in. So now I'm going to distribute this 2a, and that would be 2a bi minus 2a squared I all over n. So again, I just distributed the 2a there. Hopefully that makes sense. And then plus, and now I'm going to square this guy. So that would be b squared I squared minus 2ab I squared plus a squared I squared all over n squared. All right, that went okay. Now again, what this equals is f of a plus delta xi. That's what this equals. Now remember, what I'm trying to sum, however, what I'm trying to sum is f of a plus delta xi times delta x. So this needs to be multiplied by delta x. And remember, delta x is b minus a over n. Now, it may not appear that multiplying this by b minus a over n is a lot, but it's a lot. So I'm going to get around, I'm going to multiply it, but I'm going to multiply in a way that gets around it a little bit, or makes it a little bit easier to do. And so what I'm going to do is I'm going to multiply by b over n. I'm going to multiply this whole guy by b over n. And I'm going to sum it. And then I'm going to take the limit as n goes to infinity. And that'll give me one expression. And then I'm going to take the guy that I got when I multiplied this by b over n. And each term, I'm going to take a b out and add an a. And it will add a negative a. And that'll be the equivalent of multiplying by negative a over n. And then when I get that new expression, I'll sum it, and I'll take the limit, and we'll have our answer. So what I'm going to do now, again, in the end, I'm going to multiply it by the whole delta x, b minus a over n. But what I'm going to do right now is simply multiply all of this by b minus a. By b over n, just the first part of delta x. All right, so let's see how that guy looks. All right, and let's show it so you can kind of see what I'm doing. All right, so we're just multiplying everything by b over n. And so that's going to give us 10b over n minus a squared b over n plus 2ab squared I minus 2a squared b I over n squared plus b cubed I squared minus 2ab squared I squared plus a squared b I squared over n cubed. So I hope you are able to follow that. And I'll leave that there so you can kind of see what we did. And now I need to sum this. So all of this junk, quite beautiful junk, but junk nonetheless. All of this junk, I'm going to take the sum of as I goes from 1 to n. So I'm going to use my summation rules that were mentioned a little earlier. And so here they are here. And everything that doesn't have an I in it is, I'm considering a constant. And so this is a constant, this is a constant. And then for these guys with I and these guys with I squared, I'm going to use the particular rules that go for those guys. And some of this I'll kind of break the terms down so I don't confuse you. And so let's kind of go. So for these first two terms here, these are constants. So I'm going to be using this rule when I take the sum of a constant, it's just that constant times n. So if I do 2b over n, I'm just going to get 2b because I'm multiplying by n minus. If I do a squared b over n, I'm just going to get a squared b because I'm multiplying by n. All right, now we got this junk. And these guys have i's in them. And so I'm going to look at these as two different fractions separately. And I'm going to look at it on a separate sheet of paper, or this paper will get a little bit too messy if it's not already messy enough. And what I'm going to do is I'm going to look at 2ab squared over n squared I. And what I'm summing this, of course. I'm summing this as I goes from 1 to n. And when you do that with I, again, what you'll get is n squared plus n over 2. So, I'm summing this I, and I'm going to get n squared plus n over 2. So this is going to turn into, so I'm summing this. Let me show I'm summing this. And this is going to turn to 2ab squared over n squared times n squared plus n over 2. And I'm going to leave that like that, because when I take the limit as n goes to infinity, that's going to be pretty easy to maneuver. So I actually can leave this like this. So let me write this next. Plus 2ab squared over n squared times n squared plus n over 2. And if you kind of look at what transpired here, and again, I was just doing just this part of this fraction, and basically I have this stuff, 2ab squared over n squared, 2ab squared over n squared, and then you have the I, and the I just turns into this when you sum it. So the same thing is going to happen for the other half of that fraction. You have minus 2a squared b over n squared, and That's being multiplied by I. So when I sum it, it's going to turn into n squared plus n over 2. Okay, cool. So I've taken care of this part thus far. I still got this guy. So let's deal with this guy. Plus, and so again, I'm going to break these up into 3 different fractions. And I'll look at the first one, and then you'll be able to really figure out what the others are going to turn into. So let me just take this first part of this fraction, which is b cubed I squared over n cubed. And of course, I'm summing this guy. Like this guy is getting summed. Okay, cool. Now, so, okay, b cubed over n cubed. And again, when I sum this I squared, I get this 2n cubed plus 3n squared plus n over 6 guy. Where's my summation rule? Just to show you so you don't think I'm doing any type of tricks or magic. And so here's the sum of I squared, and it's 2n cubed plus 3n squared plus n over 6. So that's what that's going to turn into. So this times 2n cubed plus 3n squared plus n over 6. And what you should notice is that all 3 of these are going to be multiplied by this guy. So for the sake of space and time, I'm going to write each of these expressions minus the I squared, and the I squared is going to turn into this guy. So let's do that if we shall. So we'll have b cubed over n cubed. Well, I guess I'll write it as one. I write it as one fraction. So I'm contemplating it will be easy for you to understand when I do the limit if I write as one fraction, and I think you'll be able to handle it. So minus 2ab squared plus a squared b, and all of this, let me put n cubed. Let me center that guy a little more. All of this is being multiplied by 2n cubed plus 3n squared plus n over 6. Okay, and that concludes the summation. So this is what the sum looks like. And the last thing we're going to do is take the limit as n goes to infinity. Now, I just want to point out what I have here is the sum of f of a plus delta xi times b over n. So I haven't multiplied the full thing times the delta x yet. I've only done the b over n part of delta x. There's a minus a over n part that's still waiting to be utilized. So just want to reiterate that point that I haven't used all of delta x thus far. All right, so now I'm going to find the limit as n goes to infinity, and this is a very easy limit to do because you have these rational expressions. And as you may remember, when finding limits like this, if I find the power of n bigger at the bottom of these expressions, that's going to tend to 0. And otherwise, if there's not an n, then whatever I have is going to end up being, the limit. Another point, if there was the power of n was greater at the top, the limit wouldn't exist, but this limit is going to exist. So that part's not going to occur. So Let's see what happens when we take this limit. Well, the limit of 10b as n goes to infinity, there's no n in 10b, so that's just, yes, you guessed it, 10b minus, and there's no n in this, so this is just a squared b. All right, now I want to make sure you understand this because it's going to seem like maybe I'm taking somewhat of a shortcut. So imagine me multiplying this guy first by n squared over 2 and then later by n over 2. Okay, when I multiply by n squared over 2, the n squareds are going to cancel. And then the 2's are going to cancel. And there's no more n left, so it's just going to be plus ab squared. And now again, that's for me multiplying this guy by n squared over 2. Now, if I multiply the guy by n over 2, okay, the 2's would cancel. And that n would cancel, and I will leave an n at the bottom. So there will be an n at the bottom. And if I take the limit as n goes to infinity with that n at the bottom, that's going to become 0. So from this whole guy, when I do the limit, all I get is this, ab squared. Okay. And a similar thing is going to occur here. So again, I'm going to look at it as n squared over 2 and n over 2. But when I get to the n over 2 part, there's going to be n at the bottom, and it's going to go to 0. So really, I only need to look at the n squared over 2 part. All right, so n squared over 2, the n squares will cancel, the 2's would cancel, and you would have minus a squared b, minus a squared b. And again, when I do n over 2, it's going to tend to 0. Okay, now we're here. And something similar is going to happen with these. So with each of these numerators, you want to look at multiplying by these guys. And I want to look at 3 different things I'm multiplying by. So the first one is 2n cubed over 6, which is n cubed over 3. So, and before I do, I want to talk about what happens with the other stuff. So when I multiply by n cubed over 3, what's going to happen is the n cubes are going to cancel. And this stuff is going to be divided by 3. So let me look at that result first. So again, 2n cubed over 6 is n cubed over 3. The n cubes will cancel, and stuff will just be divided by 3. So this will be plus b cubed over 3 minus 2ab squared over 3 plus a squared b over 3. Now, go ahead and close this. You may say, wait, man, what are you closing it for? You haven't completed. You haven't done 3n squared over 6 or n over 6. And I'm going to do it, but I want to point out, for instance, if I do 3n squared over 6, which is n squared over 2, the n squared would cancel with this n cubed. It would leave one n at the bottom. When I take the limit, it's going to go to 0. Similarly, with this n over 6, this n would cancel to this n cubed and leave an n squared. But when I take the limit, it's going to go to 0. So this is actually all I have that's left. Well, I shouldn't say all, because this is still a lot of junk. But this is all I have. And I'm going to leave it like this for right now. I mean, you're probably saying here, well, these 2 guys are going to cancel. But I'm going to leave it like that for right now because I want to multiply by the negative a over b. Excuse me, negative a over n. And basically, what's that going to change? Well, it's going to change the sign of everything. It's one thing it's going to change. And additionally, it's going to remove a b from each term and insert an a to each term. Well, a negative a. Well, change the sign, so just an a. So, for instance, this 10b is going to turn to negative 10a. And since I'm going to change the sign of everything, I can just make this minus sign a plus sign. And what I'm going to do in here is I'm going to remove a b and add an a. So this would turn into a cubed. I removed a b and added an a. This guy would turn into a squared b. This guy would turn into a cubed. This guy would turn into a b squared over 3. This guy would turn into minus 2a squared b over 3. And this guy would turn into a cubed over 3. So I hope you can see that I simply removed a b and added an a to each term. So it's like I'm dividing by b and multiplying by a for each term. All right. So now let's see what cancels out for this stuff and really simplify this expression. So I can go ahead and cancel these out. Those two are out of there. See you later. Let's see what else happens. Now, also bear in mind that all of these items have a minus sign in front of them. So let's see. I got a minus ab squared. And let's see. Okay, let's look at this. So I got a minus ab squared, right? And I also have a positive 2ab squared over 3 and another positive ab squared over 3. So positive 2ab squared. And I guess so it's not confusing. Let me just distribute this negative sign because that part might get a little confusing. So let me do this and do that. That's already gone. And do that and do that and do that. So just so the signs don't get confusing. All right, so I got a positive 2a squared, 2ab squared over 3. And here I got a ab squared over 3. If you add those together, you'll get 3ab squared over 3, which is just ab squared. So these two add up to ab squared. And here is a negative ab squared. So they're going to cancel. And similarly, okay, here you have an a squared b. Okay, cool. Here you got a negative a squared b over 3 and a negative 2a squared b over 3. Add those together, you get negative 3a squared b over 3, which is just negative a squared b. And so that would cancel out the a squared b. All right, that cancels. And so what I have left oh, these two cancel as well. You got an a cubed and a negative a cubed. Okay, they cancel. So the only guys I have left are this a cubed over 3. It's going to stay. And this negative b cubed over 3. So let me write what I have left. So I have 10b minus b cubed over 3 minus 10a plus a cubed over 3. All right. Now we're getting somewhere. And just for the sake of beauty or understanding, I'm going to write this as 10b minus b cubed over 3 minus 10a minus a cubed over 3. Okay, that's cool, right? Now let's remember what this represented. So let me say what this was equal to. when we found this value, we were finding the limit as n went to infinity of the summation. Well, my sigmas are terrible. The summation is I goes from 1 to n of f of a plus delta x I times delta x. And again, we found that to be 10b minus b cubed over 3 minus 10a minus a cubed over 3. Okay, so that's what we found. But also remember, we stated that this guy was equal to the integral from a to b of f of x dx. And again, we found that equals 10b minus b cubed over 3 minus 10a minus a cubed over 3. And so this is a fascinating result because remember the original function. So just as a note, f of x was 10 minus x squared. And what is the antiderivative of 10 minus x squared? So let me say let big F be an antiderivative of F. So big F would be 10x plus, minus x cubed over 3, right? Well, what is this? This is the antiderivative evaluated at b, and this is the antiderivative evaluated at a, and they're being subtracted. And this is exactly what a definite integral does. So, in addition to our limit statement and what the definite integral represents, we've just shown that this definite integral, so the definite integral from a to b of f of x dx, actually equals f of b minus f of a. And remember, I've defined big F being an antiderivative of little f. And this is something a lot of people call the first fundamental theorem of calculus. And if we take this approach, and again, when I was showing this is in the context of area under the curve. If I take this approach to find the area under the function I called f of x from the integral from 0 to 3, which for all this time I've been claiming is 21, well, if we look at it, so if we actually integrate from 0 to 3, 10 minus x squared dx, we'll get 10x minus x cubed over 3, and to be evaluated from 0 to 3. And if we plug in 3, we'll get 30 minus 27 over 3, or 30 minus 9, which is 21. And of course, we plug in 0, we get 0. And so that's how we know our answer is 21. So from following the procedure of the area under the curve, we got this stunning but yet magnificent conclusion that this is what the definite integral represents. Again, with f being defined as an antiderivative, with big F being defined as the antiderivative of little f. We'll see you next time.
specialized in science and mathing. Original black men, busting thoughts that pierce your mental, the fierce, ripping your section. Vocal toe to toe, impeccable, splitting your back, son. Simple as addition and subtraction. Black thought, the infinite relax one.